It's the last lecture today on this geometry thing. Because I think it's got very advanced and there are some people cannot following, the others can. So next week, apparently, you will have some physics. I don't know what, but some type of physics, okay? So the one promise I can do is, first of all, we do surfaces. Second of all, we will program, you will see some surfaces here. You can play with your program, favorite program, okay? At the end, or last half of it, or whatever, okay? 可以，我只是说这是最后一节课了。下个星期是学物理，然后呢，下半节课我们用这个我看看，做了个曲面，用你们的最喜欢的一个 program。可以吗？这个电脑非常的。这个电脑非常的卡。我这个电脑可能。怎么又卡了？之前不是做过的吗？website called three-dimensional space。你们不是有那个什么？上次。电脑它的内存只有8个 GB。那没问题，那东西很简单。当你现在只剩下1个 GB 了。为啥？一直太热了吗？不是。还好，还有4个 GB。It's fine. These things are relatively easy just to draw, so it should not be. It's not computationally intensive. At least if you don't go completely wild, okay? OK， 所以应该是没问题的。你们可以试一试OK， 这 GeoGebra 应该是没问题的。然后或者是随便什么都可以，简单的东西，我没有说要你们算什么。But just to try out, OK? OK, so let's see. We wanted 我们是想做曲面的，我们上次做了 curves. Yes. Wait. I need to find my notes first. 有考试吗？怎么可能呢？有道理。怎么可能有？各种各样的原因不可能考试。第一，我特别不喜欢考试这个模式啊。第二，怎么可能呢？OK。是曲面吧？Is that correct? This one? Is that how it's written? Yeah. Perfect. I'm a genius, you know. Okay. So that's what we're doing today. Okay. So what is it? 你先。Yeah. 0, 1, 1. Okay, like this. Just a rectangle. Not necessarily R2. Let's consider boundaries be there, and we map it into our space, 3 space. Okay, that's 3-dimensional space, and that could look like this. Okay, I just draw some. Is that 1, 2, 3, 4? So this one is maybe smooth. Okay, that's a cap, for example. So that these red lines here are mapped to. Oh my goodness, let me. Just like this, maybe. Those are red lines, okay? So, and then I have maybe blue lines. 怎么了？长呀，那没办法。Okay, let's. Okay, 然后 these blue lines. All mapped like this. Okay. 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 So these are coordinate lines. What is this in Chinese? Coordinate lines? Huh? 网格线. Okay, yeah, probably. 网格线. Okay. So the one would be the x-axis, right? And this one would be the y-axis. And we have those lines that are parallel with respect to the x-axis, meaning the y0 is constant. And here we have x constant, and just go this way. And these lines, we're moving it to here. Okay? And now the question is, what did we do with if I would have paper, yeah, and I move it, I can bend it, right? But I cannot stretch it, right? Okay, so in this case, the length of this vector here, if I just the distance between this one and the distance between this one, that will not change because I cannot bend my paper, or I cannot stretch my paper. I just can't bend it, okay? Good. So now, the length change of each of these sectors, this is called, so it's, you would differentiate, so this is F. So for those who know, it depends on X and Y, and it would have 3 coordinates because it maps into S3, so 3 functions, right? And then you would compute what these vectors are, and I just tell you that, well, this is just Fx is the red lines, yeah, and Fy is the ones along the blue lines, yeah. Fy is this ones, and this is X, okay? Okay, so these are vectors. These here, that's Fx. This is Fy. And now we want to compute the length of that, okay? Because that would give me how much I stretched my paper, or not paper, maybe like a gum thingy, yeah, so that I can stretch, balloon or something, yeah? And that is called metric, yeah? Or first fundamental form, if you like. That's something like this. And this thing can be expressed as, first of all, the length of X, scalar product, just length of the vector, okay? Just I measure how long that is. The length of Y, I measure how long that is. And then I have something in between it, because this one might not be perpendicular to each other. Okay, so it's Fxy, Fx, Fy. So this matrix here is called a metric, because it does measure whether how long this one is, how long this one is, and how the angle between those are. Okay? Yeah? This both everything in this information. Okay. So now we call something conformal if, first of all, the Fx has the same length as Fy, meaning these two vectors are the same, equally long, and if they are perpendicular. Okay? Why are we doing that? What does it mean? That means that we stretch. You know, if I have a balloon, I can stretch and deform it. I want the balloon to have the same shape or same stretch factor in every direction. Okay? Same stretch. In every direction. Okay? Meaning then, well, length will be changed because I stretch, but the angles will not be changed. Angle preserving. Okay? So whatever angle I have here, in this case a right angle, I will keep the right angle here. Okay? That's the point. Yeah? But because I stretch in every direction the same way at each point. It doesn't mean that this vector here, these two, it's not the correct drawing because they don't have the same length, right? It doesn't mean that these two vectors and these two vectors have the same length. Just, yeah, at this point, these two vectors have the same length and they are perpendicular. But here they could look slightly shorter, for example, right? Because here you have a bigger grid and there a smaller grid. That's possible. Okay? So now, at every point, I can now say, how much do I stretch my surface? And this is some positive factor, right? Some number, at every point, a number. And because it's positive, we write it with this function, but that just means that we can call it h as well. And this would be just something which depends on x and y, which is bigger 0, not 0. Okay? And the idea is then this matrix, because these would be 0, is nothing else but this factor times the identity matrix, right? Because here we would have this function, the same function, and the off diagonals are 0. Yeah? Okay. So these are surfaces. Not necessarily conformal, but just a map of this would be a surface. Okay, we would like to just have conformal because it's not easier. Huh? Means angle preserving. Yeah, I think that's fine. Makes sense. Okay? So, if you don't want to look at formulas, you just imagine you have a square made of some balloon thingy. Okay? And now you want to stretch and bend it over whatever. You can have sticks, you can have whatever to just shape it in any form you want. Okay? The only condition you have, if you want to restrict to these deformations, is that in every direction at each point, I stretch the same way. I don't do this only, but I do the other way, the other direction equally at every point. Okay? Good. Now, we have the metric. If we would have a curve, the metric, what was the metric for curves? What was when we studied curves, what was the metric there?
Is it the area of a small piece?
But there is no piece for the curve, right? Yes. So what would be the metric? Well, I said stretch factor for the surface, right? What would be the metric for the curve?
Metric for the curve?
What did you do? So let me. What are these? What are this? What is this? Fx is. Do you know what it is? So just means that I differentiate f by x. Yes. This is nothing else but. Right? 3 rows. Yeah? So I have a vector, a direction here. What was the same thing for the curve, for plane curve? I had gamma. Yeah. What was fx there?
So the type fx is like.
How did we call it? Speed. Yes. So we computed gamma x or gamma prime, and then we took the norm of it and said it's speed. Well, here we take the norm squared, so it's not speed squared, but it's roughly what we are doing with metric, right? Okay. Good. So these are surfaces, and now for the curves, we did curvature. So it measures how much the thing is bent, right? And we said for a curve, if I have that, the bending is defined by the Gauss curvature. There's no, for Riemann curvature is far more complicated. And we said for a curve, we just fit in a circle at this point, and then we take, this thing is r, and then we take the curvature at this point, which we call kappa, to be 1 over r, right? We fit in every point a circle that fits right into this, and then we call the curvature 1 over r. Yeah? Okay. So now what could be curvature here?
So we can just think about, for points, you can just think about the planes whenever you rotate it, forms a curve, and so suppose the curve is smooth, so you can consider the curvature, and so you get the maximum curvature of that place, and the
okay.
and the minimum, yes.
Yeah.
And so you can take the product of it or the sum of it.
Yes. So what we have, let me just read. So we have this direction, these red curves. For these red curves, we can do curvature. Yeah? Because we just fit in a circle, which is in the, well, it's really, really bad to fit a circle right, on the curve in R2, right? R3. So how do you find the proper plane? Well, you choose the tangent here, and then you choose one direction that is perpendicular to the surface.
Yeah.
Then it defines a plane where your curve lives, and then you can choose a circle on the plane that fits best with the curve. Otherwise, it's not possible. Yeah? Okay, so you do this. And for the red curves, you do that for the blue curves. What you get at every point is two curvatures. Okay? And how it's written is, as before, we differentiate twice. For the curves, we differentiate also twice because we wanted how the speed or direction change was our curvature. So change of the direction, which was gamma prime, we take a second prime. It's the same, just that we have now two directions. The one prime goes in x direction, the other prime goes in y direction. So that's why I'm writing it this way. But it means just the same. And this means that I take the plane that is given by n and the tangent plane. So that's what I explained before, that you have to choose a plane where your circle lives. Okay? So this is one. This is the other. But then there are mixed terms because your plane might actually change, right? Two things. So this is something we obtain, and this is called the second fundamental form. Yeah. There's the first fundamental form, which was the metric, and the second fundamental form, which is something that has to do with curvature. Okay? One, how to measure the distance. Set two, how it's bent. How much we stretch and how it's bent. Yeah? Two things. Okay. Now, when you have that, you see, for those who had linear algebra, this is a symmetric matrix. You can have a diagonal. You can diagonalize. Yeah? What is diagonalize in Chinese? Because it's symmetric. Yeah? So we can find some basis so that it's kappa 1, kappa 2. And why do I write this here? That's because we have stretched, right? For the curvature, we were defining on arc length parametrized curves. Yeah? So now, when I take this, I can define Gauss curvature, Gaussian curvature. Which is just a product. And mean curvature, by the name, is just a mean. Yeah? So, when we are on the surface, this means, if you just forget about anything, we have two different types of curvatures because it depends on in which direction we look, right? Yeah, because this will have a different curvature than this. But it turns out that most of the directions, or actually only two directions matter. The one where it's maximally bent, and the one where it's minimally bent. Okay? Everything else you can get as linear combination of these two, so it's less interesting. That's a major difference. Okay? So we have a lot of curvature, but only two matters. And of course, out of these two, we can get all of it. Okay? So now what does Gaussian curvature mean? So there's a famous theorem, Theorema egregium, the beautiful, I think, theorem, right? No. It's some. So out of the time where people were still writing in Latin, okay, I think it's just something like beautiful. Theorema, I mean just theorem in Latin. Egregio means beautiful. Or something like that. it says that the Gaussian curvature here only depends on this part. And so only depends on how it's stretched, but not on how it's bent, which is weird because it's a curvature term. Yeah? Only depends on the functions there, you have to differentiate, but not really on 2. Okay? So when Gauss proved it, it was hard, you had to do lots of computation. Nowadays, it's tautology. Okay, it's just definition. But at that time, it was very difficult to see through these formulas. So basically, it says mathematics developed, and it's great that it developed because now these things becomes easy. So originally, in surface theory, people were concentrating on this one. That had this beautiful theorems, right? This one were not less interesting. Now, when we did this experiment with soap film, right? You remember? We had minimal surfaces.
Yes, minimal surfaces.
And minimal surface. So when minimal surfaces appeared, mean curvature came into the game.
Yes.
Right? Because mean curvature, minimal surfaces meant that mean curvature is 0. So this is called K, and this thing is called H. Yeah? I don't actually know why. Yeah, this thing is nervous. I don't know why. I have no idea why they chose these names. So when you have a soap film, you will always have mean curvature 0. Okay? And today, the idea of today is that we write down surfaces which has mean curvature 0 so that you can play on your computer there and try to draw them. Okay? We had them somehow using soap films. Now let's see how we can draw them on the computer. Okay? Okay? And then let's see how many different shapes you can find. But we may need a little bit of theory of how to do it properly. Okay? So we would like to draw minimal surfaces. Meaning something with H is 0. And we want also the construction that this thing is diagonal. So we really have something conformal. Okay? This is a function. I mean, I could just write it here and here, yeah? Like this. It just means that the one direction is equal to the other direction, and they are perpendicular. So the stretch in all directions are the same. Okay? Good. Questions? No. No? All is good. Okay. So let's look at minimal surfaces, and we have H equals 0, right? In this case. That means if I just add these numbers, I would have 0. Yeah? This and that, there's factor, but I don't care. So meaning, yeah? Okay. Now, I would like to say, because of that already this is 0, which is a Laplace. Mm-hmm.
Yeah.
True? Is that true?
为啥那个 f(x(x) 大于 y(y) 和 n 不能垂直呢？
不，就是这个是0，是吧？因为我们说的是 h 是0，我就是说这两个加起来是0，那么就是说这两个加起来是0。可这个是这个，这个是这个，是 f(a)y(y)， 所以这就是一样的，就是这个，就这是一个。Maybe first fundamental form is diagonal. Now I claim this is true. Yes? Yes? Why? 是，就是 Huh? Yes. You can think about it. You can think about it. Let's go from here. Laplacian is 0. Okay? And I'm sorry, I'm introducing something now which will lead to formulas, I promise. But right now it might be more difficult. Okay? So, you can think about this one, okay, why this is true. But let's focus on this now. So, instead of minimal surfaces, we are trying to find some harmonic functions, right? This is just a name. Yeah. Yes. So now, one way to do it is doing analysis. Okay. The other way to do it, why harmonic functions are important, is doing complex analysis. Why? Anyone know what it is? And why it's, what is the relationship to harmonic functions? Do you know? Ever heard about it? Nope. What is the relationship then?
I don't know so much about harmonic functions, but I do know about complex analysis.
Yes, but
Studying functions on C.
yes. So basically,
Because C is really strange because the field is tangent of R, and also it's algebraically close, so something strange works.
well, it's not big. Well, so complex analysis is, well, let's do it this way. I introduce something like Z, which is x plus a I y, meaning every point has two coordinates, x and y.
We just learned it there in our
Like, so it's a point in the plane, like this one would be maybe a half and 1. So this z would be a half plus I times 1. Okay, that's how you write it. Okay, now you can differentiate z. And just like differentiation with x and y, this should be 1. And you can differentiate with something called z bar. Is just minus. Yes, so instead of this vector, I would take the reflected one along the x-axis. Okay? But if I take del bar z, I have 0, and del z, z bar is also 0. Okay? This is just a definition. Whenever I use this, it just means this. You don't need its differentiation, but still. Now, the idea is if I that give me a function h of the form constant plus or a0, a1z plus a2z squared plus a polynomial or a series in z, then this thing is called holomorphic or complex differentiable.
Oh, I got it. So it's
Because del z bar of h is 0. Okay? Because there's no z bar in it, so if you differentiate, this is so-called constant in z bar, this would be 0.
And then also Cauchy-Riemann.
Yeah, that's Cauchy-Riemann equation. That's everything. Okay. Okay. Now, this basically it says, okay, we now have z and z bar, which replace our x and y, but when I see no z bar, then it's 0. It's constant with respect to z bar. Okay. But the key point is, if I take the real part of h, that is harmonic.
Oh, I got it. Oh, yes.
On the other hand, if
Yeah, so so this say is really complicated, and if one is holomorphic and one, so it's actually just like smooth, and so for example the functions given each the power negative 1 over x squared. That's given in our class before, and so this function is smooth but not holomorphic.
yeah, there are many of those. So the real part, sorry, I should explain, means I write everything with x plus iy. Okay, like in here. So x plus iy squared would be z squared. That is x squared plus 2ixy, but then I times y squared, and that gives me a minus y squared, and so on and so forth. Yeah. So now you see, I can take the real part of it, of this one, for example, that would be x squared minus y squared. Okay, because it doesn't have an I. Okay, so I do it here. I plug in everywhere my x and y's, and then take everything that doesn't have an I in it. And that's my real part. And this function will always be so-called harmonic. That's all. This thing is, it should, oh, there are multiple now. They should just leave the classroom. Okay, so there's the connection between harmonic and holomorphic is the real part of a holomorphic function is always harmonic. And if I have harmonic, I can extend it to a holomorphic. Okay? You can think about how to do it. But this is what I want to say for now. So now, if I want to find such a thing, okay, I can consider this one should be rather something like del z f. Now, in this case, we need to define what it is, and it turns out del z is just 1/2 del x minus I del y. Okay, but it's something. Okay, it's a derivative of something, and it's supposed to be holomorphic and satisfy. I promise this is the last bit of. This, because this one would be, it's F1, F2, F3, right?
Yes.
Which is equivalent to conformal to this set of equations here. If you replace x and y with z. Okay, we will talk about it later. But what I really want to get to is to solve this equation, and then we can play with z's and having surfaces. That's why you can think about why this holds, but let's do it later. Okay? So now what we need to find are functions of this form satisfying this. Okay? And if we did that, when we do that, then I didn't explain everything, so don't be shocked. That the point is we want to do that, and if we have it, if I have an f doing that, I can take the real part. I can integrate. Okay. And that would be my f, which automatically would be my minimal surface. Okay. So I solve this equation. I have some idea of how to get my minimal surface. Okay. Now, and I can write, since this equation only requires f1, f2, f3 to be holomorphic, so of this type, okay, I just can try to solve it. Okay, claim, or maybe, okay. Does this equation remind you of something? What? What we had actually in this class, okay? We had something in this class, we very, very much looked like this equation. And you should have that in some algebra class or whatever as well. What do you think was it? Let me maybe add an I here, like this. Maybe help. Does that help? It would, because that doesn't change anything. And then what do we? What is this equation then? So I would have f1 squared plus f2 squared, f3 squared. What is it? Ever see such an equation? Yeah. Yes. Why am I saying that? Ever thought? Okay, so these need to be power series in Z, like this. But when you want to solve this equation, you have this problem, you have to take a square root, right? You know that f3 is the square root of f1 squared plus f2 squared. But if you take a square root of this, it's not necessarily a polynomial anymore. So you have a problem, right? So what this does, or the question here is actually the same as to find. So this, in Pythagoras, there was a question about find integer solutions, right?
Yes, we had talked about in our number theory class.
Yeah. So meaning, for example, 3, 4, and 5 would solve that, right? So the question is, so 3 squared plus 4 squared, right? Although we have to take a square root here, we know somehow we can take it, and it still is an integer number. Yeah? So now we want to solve the same for this. So can we, do you know, maybe you should have learned it, how to find integer solutions for Pythagoras? And how to adapt it to find integer solutions for this.
A squared minus b squared, 2ab, a squared plus b squared.
Can someone write it on the blackboard? 中文. Then you explain it to him in Chinese.
这是一个公母定理，是我们一个在我们数学课学习的，数学课上也学的学习转化解方法。数学课上也学。2a 比 a 减 b 方 a 方加 b 方。
Write it, please. Okay, great. Good.
We want to know about the solutions of holomorphic one. So
Yeah. What does it have to do with this? So let me just, what he wrote was the following. Obviously, we have one solution. So we have two freedoms, right? We can give two and get the third one. So the question is how to find two integers so that the third one is also an integer. Yeah? So here the answer is you give me a b integer and I put it into this form. So f1 would be 2a times b. f2 would be a squared minus b squared. And f3 is then this one. And in this way we get all the integer solutions. Okay? Okay, so now what has this to do with solutions of that for holomorphic functions? You know, 这完全没用。没学是吧？我认得很多人都会用手拍，直接从后面这样。我不会啊。呀，苍蝇在这儿的话，从这后面这样子。
经常会搜一道气。
You can try. I mean, yeah. Always be angry. Okay. Let me. I mean, I want you to have lots of time with the computer. So let me just give the thing. So we do exactly the same, except for since we have the f3 was I times, have this I, yeah. And I write it in a slightly different form. Because I want this have meaning, but it's so. Okay. Because in this way, G has some meaning. It does not matter that I write it this way. It's exactly the same formula. The I is because of the minus before. And f3 is G times H. Exactly like this, right? It's the same formula. The point is, if G and H are holomorphic, then all these things are holomorphic, and we satisfy this equation. That with the minus, yeah? So this thing is called bias stress representation, okay? What is the advantage of this? Okay, let me just give you the advantage of this, and then we can try it out. This thing is called bias representation. Yeah, for minimal surfaces, what you do is you give me a G, you give me an H, okay? Then we get a minimal surface. Get a minimal surface. Yeah, that's all. Through this formula, you put it here. You give me G, for example, Z. 1 over Z. Okay? It's not quite from it. The domain is just exclude. So for example, this and that. Okay? I put it in here. I get some functions, F1, F2, and F3. Okay? So it's a half, oh my goodness, Z minus 1 over Z. I have Z plus 1 over Z, and I think G times H is 1, or I. Maybe there's an I here. You should check whether it's 0 or not. Okay? Okay, now we can integrate. Right? And then take the real part. So this one becomes a half z squared. Okay? This one becomes log. Okay? And this one becomes z. Right? So that's the integration. And then you have to take the real part. So z squared, you do what I had here and take the real part. X, this would give x squared minus y squared.
Log do not have, or
Yeah.
the log function do not have
It's not well. No. So you have to change your domain. It's not C. Yeah? But that's fine. Okay. So now you can draw a little piece of a minimal surface just by this formula. Okay? So basically what you need is to find any z squared, if you like. Whatever, just think about something. Put it into the formula, do this. But let me show you something which is fun, which is you multiply this here with some number. Constant number, which this here is just a point on the circle, like this. Now this is 5. So if I do that, I add at every component here this factor, but I don't change this equation. I don't change the integral. But because I changed the thing, I changed the real part. I get a different surface. Yeah? This is called associated family. So whenever I have one solution, I have for every angle another solution.
Yes. We have infinitely many solutions.
Infinitely many solutions. Okay. So now let's go on, try it out. So can someone help her? I think this is wrong.
是下课了。
没有，我叫他，我们在。
做到一个几小时。
通常我们不然待会儿，但是就是。
Help. You should help him. You should help him do it. Is Desmos better? Which one is better to draw 3D pictures?
Georgebra is better.
You think Georgebra is better?
Yeah, Georgebra is better. Yeah, 3D. Okay.
Good.
I'm familiar with.
Okay. That's.
卡崩的吧？不吧，不至于，计算机没演。
So.
还有4G 呢。
You can put, so you should take take your favorite whatever.
OK， 那我们还是先把这个 x1 好吧？
你直接想就行了。对，人只是这份9
哦 ，Chinese。
别呀，
点一下就行了。
哦，
I'm familiar with Georgebra.
So excited. Good. You need to check the formulas first that you type it correctly.
Yeah. So we will first define that g of xy, where we see z as x plus y.
Yes. Can you do complex computations?
As
X plus x, come on. Desmos can? Good.
Yeah.
it's what?
他默认为这个挺奇怪的。
So let's just define that g1 xy equals x. But actually this has a better feel for the better feel. H or H one. H2 XY.
Plus y squared. X.
What?
X. What's this?
No. What do you mean? X.
Yeah. Yes.
What's that?
No IY. No IY.
那我们需要，不是你按根号负一打不行吗？
不能。
不能。
我 Desmos 支持 ，Desmos 是支持的。
但这个看起来的效果会更好一些。
是。
好吧。
适用版本。有加我版。Desmos 那个3D 器自动图的这个，特别不易出，就是特别多方不去出。
可以。
Hidden.
And so we should just consider
Let me check whether my equations are correct without the i's and so on.
So
I think before you type it in, you should compute it first on paper, because otherwise it's very hard.
But we can use integrate this.
Sure.
Wow.
Maybe the others can try to compute the thing what you have to put in here on paper,
Yes.
and then tell him what to do.
I think so.
Once you set it up, then it's easy the second time. You can compute it actually on paper. There's no problem with that.
Oh, by the way, I just found out that there's the complex number part, and so you can just use it, not and so when we whatever.
I think there's no I here.
I
This is good.
I got it.
You have the formula?
We do not need to. We do not need to calculate it, and because we have this.
So let's see how long it takes. 把这个，我们剩下就只是玩了。